Right, this video is on single replacement reactions in the activity series. We'll be working off of this guided note paper, and then the activity series as a cheat sheet. And it should be on the back of your solubility rules. That's for another discussion. Today we're only talking about the activity series. Okay, so this idea of the activity series, it governs single replacement reactions. And so we've already learned about single replacement reactions. They occur when one substance kicks out or replaces another. And we've also learned, maybe not in huge detail, but this will be a huge piece of information today, so I'm going to put a little star next to it, that metals kick out other metals and nonmetals kick out other nonmetals. So we're going to see that in great detail in this lesson. So, okay, what is the activity series? Well, it's basically a list. Okay, oops. And as you can see, there are actually two activity series. Okay, there's an activity series of metals, so you notice all of these are metals. And then there's an activity series of nonmetals. And you'll notice that the nonmetals are really only the halogens: fluorine, chlorine, bromine, and iodine. But so there are actually two different activity series. Most of the time we end up referencing the metals, but once in a while we see a nonmetal activity series reaction. So what is it? It's basically a list of metals or nonmetals in order of, let me say this correctly, it would be decreasing, I guess, decreasing reactivity. Okay, so what does this mean? Well, so if you go to this paper, I keep getting turned around here. Okay, if you go to the activity series paper, let's look at our metals activity series. So at the top, we have lithium, rubidium, potassium. So these metals are very reactive. So I would even go ahead and write that. You can write that right on here. Very reactive in terms of the top of the chart, while the metals at the bottom, gold, silver, copper, are not very reactive at all. So I would go ahead and write that in this space. So very reactive and not very reactive. And in your nonmetals, it's the same thing, although the chart is so small. Fluorine is very reactive, while iodine is not very reactive. Okay, so high reactivity, low reactivity, same thing over here. So that's what the activity series is. And if you think about it for a second, it kind of makes sense, because if you look at the bottom of the metals and who the metals are who have low reactivity, they're things like copper, gold, and silver. Well, what do we make out of copper, gold, and silver? A lot of things. We make jewelry, we make coins, and so the reason we make those substances out of very non-reactive metals is because otherwise our jewelry and our money would be reacting with substances, and that would be a bad thing. And so it kind of makes sense if you step back and think about the fact that those metals are your non-reactive ones, and they're the ones we make so many common substances out of. Okay, so let's do an example about how this works. You should have room on the front of your paper where it says activity series. So let me erase this, and actually let me add something. Okay, so how does the activity series work? I'm going to say only a substance okay, I'm going to amend this. Sorry, I'm going to add this. Only a more reactive substance can kick out a less reactive substance. Okay, big idea. Big takeaway point in this part. That only a more reactive substance can kick out a less reactive substance. So what does that look like, or what does that mean, and then what does that look like? So if I go back to my chart, what this means is that, say, barium, okay, who is more reactive than zinc, right? Again, it's closer to the top. So barium would be able to kick out zinc because it's more reactive. But the reverse is not true. Zinc cannot kick out barium because it's less reactive. So that's how the activity series works. So let's look at an example, and then we'll do some practice. And then that's it. That's really the idea here. Okay, so you should still have some room in this blank space right here. Okay, and we'll do two reactions. So let me just make something up. Let's say we have, I don't know, magnesium. So I'll do an example. Magnesium plus hydrochloric acid, or HCl. Okay? So my question, of course, this is a single replacement because I have a single thing. And so my question is going to be, can magnesium kick out, in this case, it's going to be the hydrogen because magnesium is positive and hydrogen is positive. So can magnesium kick out hydrogen? That's the question. So I always draw a little arrow. And I'm questioning this. Can this happen? Can magnesium come in and kick out the hydrogen? Well, up until today, we didn't know the answer. And so now we have to consult our chart. So we're going to find magnesium, and we're going to find hydrogen. Find hydrogen. Hydrogen's all the way down here. So can magnesium kick out hydrogen? Yes. Magnesium is more reactive. So yes, this happens, okay, which then means I'm going to treat this like a single replacement reaction. Magnesium comes in, kicks out hydrogen. Hydrogen's now by himself. Remember, solo at the dance, except actually hydrogen's a diatomic, so it's H2. And then who gets together? Well, the magnesium is going to get together with the chlorine. We have to be careful with our charges. Magnesium's +2, chlorine's -1. And so my formula should be MgCl2. Okay. Now my reaction is not balanced, but I can fix that quite easily. I have 2 hydrogens on this side, only 1 here. Putting a 2 there will fix my hydrogen problem. Gives me 2 chlorines. I have 2 chlorines, 1 Mg and 1 Mg. So this is the reaction. And if you did this reaction in a lab, and we would expect it to happen, we would expect to see something because based on the activity series, we have learned that magnesium can in fact kick out hydrogen. Okay. So what about a second example? Let's do, I don't know. Okay, so what if this was your second example? And this time, I have my single lead, and lead's a metal, and lithium's a metal. So lead's trying to kick out lithium. So can lead kick out lithium, right? I don't know, so we go to the chart. Can lead kick out lithium? No way, right? No, it's way too non-reactive. So this is not going to happen. Sometimes I draw it like this and say, oh, nope, can't happen. Lead will not kick out lithium. So in this case, what happens is nothing. Nothing happens. And so we don't get products because we don't make anything new. And so instead we write NR, which is shorthand for no reaction. So if you did this reaction in the lab setting, if you put lead into this substance, you would see nothing because nothing will happen. And so what we have now learned is that sometimes in single replacement reactions, we can get a reaction, but sometimes we can not get a reaction. So sometimes we have no reaction situations. So this is the first time that we have learned that sometimes we can mix things together and nothing happens. And there's a reason for why it doesn't happen. And the reason we're learning today is all based on the activity series. So let's do these practice problems together. There's a handful of them. And we'll see how it goes. Again, remember, anytime you can pause this video and try them on your own. So give me just a second to get these written. And so at this point, it's you definitely have to have a activity series to do this with. We have to know if, they are more reactive or not. Okay, so here we go. So again, we're going to be consulting the activity series through this process. And we're either going to be able to say, yes, it happens, and write products and balance, or we're going to have to say, in R, it doesn't happen. So the first one, can silver kick out potassium? I know it's potassium because it's the metal. Silver and potassium are both metals. So can silver kick out potassium? Absolutely not. When it's absolute, and you don't have to do this, it's just my notation. Since it cannot kick out potassium, it's an NR, and we're not. No reaction. Number 2, zinc kicking out silver, right? Remember, metals kick out metals. So can zinc kick out silver? I don't know. Let's go to the chart. Can zinc, there he is. Can zinc kick out silver? Yes. So this one should in fact happen. And let's think about what happens. So if silver gets kicked out, silver's all by itself, and zinc and nitrate get together, but we have to deal with charges. Zinc is one of those ions who's always +2. Nitrate's -1, so this is ZnNO3 and of course now I need to balance. So let's see. I have 2 groups of nitrate. I only have 1 group of nitrate, so putting a 2 right here fixes my nitrates. Also gives me 2 silvers, so putting a 2 here gives me 2 silvers, and there you go. Remember, these are 1s. All right, number 3. Now this one's written kind of in reverse, so don't get fooled. Remember, it's always the single thing that's trying to do the kicking out. So can aluminum kick out hydrogen? How do I know it's hydrogen? Because they're both positive. Can aluminum kick out hydrogen? I don't know. Let's look. Can aluminum kick out hydrogen? Yes, absolutely. So this should work. The hydrogen's kicked out by itself. It's H2 because it's a diatomic. It's not H2 because there was a 2 here. That's from charges. It's H2 because it's a diatomic. And then who got together? Aluminum and sulfate. Aluminum's +3, sulfate's -2. So let's see. Al2 SO4 3 is my formula, and I need to balance. I have 2 aluminums. I need 2 aluminums. I have 3 groups of SO4. I have 1 group of SO4, so putting a 3 here fixes that. It also gave me 6 hydrogens, though, and I only have 2, so if I put a 3 right here, it fixes the hydrogens. And that equation is now balanced. Again, if you did that reaction in a lab, you would expect to see something because based on activity series, it says this should happen. Number 4, can copper kick out iron? I don't know. Can copper kick out iron? No, it's less reactive. So this one doesn't work. And remember, anytime it doesn't work, it's an NR, which stands for no reaction. All right, and then the second set of 4. All right, so in the second set, let's see. First one. So this one's different because this is actually your, where to go? This is your halogen activity series. So in this case, the single thing is chlorine. So this question is, can chlorine kick out iodine? See, now we're in non-metal world. Non-metal, non-metal, or a negative charge thing and a negative charge thing. So can chlorine kick out iodine? Same rules apply. Can chlorine kick out iodine? Yes, it's more reactive. So who's by itself? Iodine, who's a diatomic, so it should be I2. And who got together? The Mg and the Cl. Think about your charges. Mg is +2, Cl is -1. Formula is MgCl2. And I believe this thing is already balanced. Yes, it is. So I'm done with that. Number 6, aluminum's the single one. So the issue is, can aluminum kick out lead? I don't know. Can aluminum kick out lead? Yes. So who's by itself? The lead that got kicked out. Who got together? Aluminum with a charge of +3. nitrate with a charge of -1. Oops, that should be a 3. Right, I need 3 of them. Notice that the 2 didn't come with it because that was there for the lead's charge. So this is where it gets very tricky. You have to be very careful. And I need to balance this reaction. This one's a little interesting. I have 2 groups of nitrate. I have 3 groups of nitrate. 2 and 3 should make you think 6. So I need 2 to give me 6 nitrates. I need 3 to give me 6 nitrates. That gave me 3 leads. And that gave me 2 aluminums. So there's that one. Number 7 is another halogen situation. So chlorine is the one who's by itself. Can chlorine kick out iodine? I think we just had this. Can chlorine kick out iodine? Yes. Iodine's by itself. It's a diatomic. I2, Na, and Cl get together. Not Na and Cl2, but Na plus and Cl minus, which of course is salt. Right? I always go back to my charges. I do need to balance this. 2 chlorines, only have 1, so a 2 here. That gave me 2 sodiums. 2 sodiums, that gave me 2 iodines, 2 iodines. So I'm good. And my last one, aluminum's by itself, positive. Can aluminum kick out hydrogen? Can aluminum kick out hydrogen? Yes. Making the hydrogen by itself, diatomic, H2, and the Al and Cl getting together. Think about your charges. Aluminum is +3, chlorine is -1, so AlCl3. I need to balance this. Let's see. Kind of messy. I have 3 chlorines and 3 chlorines, so if I put a 3 here, well, that gives me 3 H's, and then I have 2 H's, and this gets a little ugly, so that's not going to work. Knowing 3 and 2, I'm probably going to need 6 H's. So if I put a 6 here and a 3 here, right, that'll give me 6. My H's are good. It gave me 6 chlorines. I have 3, so if I put a 2 there, I have 2 aluminums and 2 aluminums. So there it is. Balanced. And that is single replacement reactions in the activity series. And so when you see a single replacement reaction from now on, you should be asking yourself, can this reaction occur? And the only way I'm going to know if it occurs or not is if I check my activity series.